Okay, this talk is about computer vision. I split it up in a couple of very simple topics that require me very little time to explain. So mainly like old-style image classification, feature detection, how it used to be done, how it can be done now. As Shadi mentioned, some improvement on face analysis, detection, recognition, generic purpose object detectors, and always useful semantic segmentation. And then my colleague Mikayel is going to give an example about how to build something useful out of all of this in a specific case of text detection in the wild. Okay, let's start. So you may have noticed that since version 10 now, we have a complete, fully automated, yet customizable framework to do image classification, which is built in within Classify. So what happens, typically, I don't know if you ever played with this, you can have data like this, and you can say, oh, I have like a bunch of classes, a bunch of images, and I want to train a classifier, and you just put the data in. I just picked a method here because I wanted to control what it was, and then what I'm going to do now is I'm just going to import them because we don't have time. This is like 5 minutes, but I don't want to waste this time. And these things here gives a classifier function, but you can use like any normal function. And that's it. Like this is what you need to do image classification with this very, very simple built-in framework. Another very good feature that I hope everybody is using, but I'm always repeating that in every talk because it's very nice, is that you can plug the function into a measurement function that will pre-compute all sorts of measurements, and then you can query them, like I'm doing now, to see what's going on, basically. Huh. Nice, full screen thing. Okay, very small. I don't know if you can see that. This says, for example, that we got 84% accuracy. This is a 10 classes database that I trained with only 300 images per classes because my laptop is not that powerful. And it's already pretty good with this amount of data. And of course, since a bit more recent than version 10, we support, we have a fully functional high-level, very simple to use neural network framework. So I put this code here that generates a simple convolutional net. I'm not going to explain this. It's the usual stuff. If you have questions, you can come to me later. Yeah, please?
In the logistic relation before, what are the features?
The images. And if you wonder like, how do they become data, the built-in feature destructor for images is using ConvNet to convert them to an embedding space. You can do whatever you want. You can specify the feature destructor. I think the default one is using something like this, but you have no control. With this thing here, you can define your own network, and you can do whatever you want with this. And what I did yesterday is I took that network, this code. Actually, I was using the built-in Cypher 10, so I just need to put this string in to do this testing training. I don't even need to copy data. This will be taken from the cloud. And I say validation set automatic because this resource data has some testing data built in. And then I say train on GPU, which will not work here, but was working on Amazon. And I set the batch size because something I wanted it to train very fast. And what happened, basically, if I import this, it happened this. So this is, again, very small, but it says that it trained in 5 minutes. And it's a pretty fast network now. So it is like 7,000 examples per second on that GPU. So it's way more than real time there. And again, I can import the classifier measurement, and I see that with this network that I put together with Carlo while we were drinking coffee yesterday, we got from 80 to 89% accuracy. Of course, if you study this a bit, and if you work on your architecture, and you do proper data augmentation and whatever, you can do even more. And right now, this is like all standard stuff for image classification. So I'm going to go very fast with this. This was old-style feature detector. I mean, before neural networks, what you would do is maybe histogram-oriented gradients plus support vector machine was a kind of one of the best performance thing. The idea is that you take the gradients of these images, you check the orientation, you do the histogram. A face is going to have a different histogram than a random patch. So then you can, again, compute some features. Let's see if I can show them here. And you set up training data, and then you run it to classify with support vector machine. This is 3D graphics, which is ruin everything. Okay, here. These are the features of the oriented gradients. Not gonna turn it. Sorry. Okay. And what's happening here, basically, if I can scroll, I shouldn't have customized the built-in style sheet. What happens here, if you train this, is that you get this nice classifier, but I should probably retrain here because I broke it with the other one. And this is to show how this works basically in real time. You look a bit at, also other training data. Okay, this is a note for myself, use different names for different variables. So this is how you train a classifier in real time. And this has useful metric. Like this is a very short training, it's gonna be like 20 seconds, but this can go on for minutes, hours. It's gonna tell you how it's going, and is even gonna try different methods. Right now it's support vector machine, so it's trying different parameters within the same method. And of course you can query it, you can extract everything, and you can even force it to use specific parameters. And once this is done, you can try it on, for example, the crops and say like, okay, this was very bad training. It used to be 0.6 this morning, so this is what you get for not setting it. But you see that the probability of something being a phase crop is very different in this case than in this case. Of course, if you fine-tune it a bit. And this was like old-style cascade classifier. You take an image, you split it in multiple patches, and this is what you get when you apply it. So for example, these are like my random classifier was able to pick, to do a simple phase detection old style. Of course, you can even train a network to do that, and it's also much faster. And this is something I trained with a colleague of mine that is doing the same thing, but is using neural networks to, instead of doing custom handcrafted priors, is training the features on the dataset itself, the feature extraction procedure. This works relatively well. To do all of that, and we need good feature extraction capabilities, which in turn, they are also enhanced by the use of proper neural networks. So this is what we could do before. It's the red thing. I'm sorry for that. But now we are doing the green thing, which is so much better. And this is what you get with enhanced capabilities in your network for feature detection. Because in old style cascade, what I showed you before, you needed to really focus on a tightly defined problem. Neural networks can learn a wider variety of features. In this case, they can learn to detect faces in any orientation, for example. And this is also reasonably fast. So you see, if I turn it, then, it kind of works almost all the time now. But what do you do once you had these detections? Okay, one thing you can do, for example, is run a bunch of networks. So I recently retrained the age network. It's a little better, a little more honest, even if I'm not sure if that is a good thing. Then you can get, for example, sex. Emotion is another kind of standard play thing to test these kind of things. And another thing you can do is, of course, landmarks. This is very useful for morphing, alignment. All these fancy phone apps that you have are using something like this. Or what Carlo just showed for audio, you can do it for faces as well. Yeah, you can embed each image in a custom descriptor. And if you know what I'm talking about, you may know what this is going. Then using this descriptor, you can do some sort of recognition. So okay, I give you Bush. Oh, where is Obama? I swear I had also Obama here. I don't know where it went. It's not a political statement. So what this thing is doing is getting the images for my example feature set. It's looking at the embeddings, comparing them in the embedding space, and says, okay, this person that you have here corresponds in the feature space is very close with this person here. So I'm going to give the label Bush with this probability, which is very high. And if I remove one Bush image, for example, the probability is high, but not that much high. I lose it a bit. And of course, the more images that you have, if you have a Photos app on the Mac, the more images you add, the better it is in suggesting, oh, is this you here? Is this your daughter? Do you want to search all the images with your mother? I don't know why, but. So you can build applications like this. And then there's a free-form detection. Like this was all tightly tailored to faces, but you can do stuff like this. Yeah, same image, and this is what you get out. And okay, these are people, these are objects, and of course we have a lot of convenience functions, so you can directly plug it in, highlight image, it will compute it on the image, and bam, you show something like that. And if you have a decent network, this might even work real time. So let me try. I don't know if this thing is going to work. So this is a video of a dog, which is annoyingly slow. Okay, this dog is crossing the camera. And what I'm doing here, I'm using another convenience function, which is called image contains queue. But it's like, does this image contains dog? Maybe. Okay, this is what happens on my laptop, which is not super real time, but you see the image turns green when you have a dog. So you can use it, I don't know, like, is my baby still in the camera? Maybe, yeah, I hope so. And, oh, yeah, I promised cat in the summary. I don't know if you read that, so you can even detect cats, of course, because if you don't have cats, it's not serious image processing applications. And, okay, let me end on a more serious tone here. What's semantic segmentation? Another cool computer vision applications. Basically, you want to assign a meaning to every pixel in the image. Why this is important? Practical example is medical imaging. Yeah? You have a brain scan, you have something like, you have tons of these scans, and you want the doctor to only look at the important one. Or maybe when you're not sure. So it would be great if you could filter them, pre-filter them with the network. And what this thing is doing, for example, if I load this nice called UNet model, because it compresses and uncompresses, I mean, it has nice U shape if you visualize it. And then I get an image. And then what happens if I evaluate this mask, these networks on the image, it creates a mask. And okay, this was Mikayel's mask because I ran the whole notebook before, which is not related to what I'm going to show. So this takes a bit of time because it has to, first it downsample the image to collect all the features. And typically you end there, but now I want also to upsample to find out what the correct mask is. And if I visualize this together, so basically, this is what a doctor could get. I don't know if you can see that. Yeah. So the idea is like, oh, take a look here. This cell might be problematic, or like, oh, this is a regular thing. Like, I'm super sure. Let's skip it for now. So like this was just a very quick overview of stuff that you can do with our computer vision-related functions in the language. And for more practical applications, I'll just leave the floor to my colleague Mikayel, please. That's going to talk about text detection. Thank you.
Can you hear me? Yeah. Okay, great. So, all right. So Giulio explained like what we have in sense of object detection. So text detection is a custom case for object detection, which is quite trendy now, and because we have like a lot of need to recognize the text, but to recognize it first, we need to figure out where it is. And it can be problematic because the text can be like skewed, warped, and it's not very trivial problem. So, oh, okay. Okay. All right, so we will be introducing a new function which is probably going to be called find text, and it will basically allow you to extract almost all the possible features you can describe the text on your images, which is basically all possible variations of regions. It can be, oriented bounding boxes, which is basically parallelograms, or normal bounding boxes, skewed angles, the strength of the recognition regions, and this is pretty much enough to do. So just to see a few examples how this thing looks, we can see, for example, like this is an example that Shari also showed. So basically, we are extracting the image and aligned image with some descriptive properties of the text that is located on the image. And we can do the same thing on various type of images, because we have basically scanned images, natural images, we also have web images. So, but if we try to classify them into two groups, we have only natural images, which kind of semi-includes web images, and we also have document type images, which is scanned images. So this is going to work on both of them as well, within the same quality. So we can do the same thing on different levels, which gives us room to drill down from to character level and expand to, right now this is line, but this is going to probably be extended. Right, so as usual, and as the other functions that are present in Wolfram language, we're going to provide you with options that will help you to figure out, you know, like what you need for your very custom case. For example, like I'm not going to list all the options because like we have more than a few dozens, but maybe the most interesting and useful ones. So for example, one is acceptance threshold that allows you basically to, you know, like filter out the detection based on the level of confidence, let's name it this way. Another very useful thing is method. Actually, the function is going to be very smart, so you don't really need to tell if this is, you know, like scanned image or natural image, because we have an internal classifier that does the job for you. But if you are like super sure you are smarter than the classifier and you want to specify this, you are free to do it with the method option. Just for now, I want to show like the detection results. Both on a raster image, which is basically a document type of image, and on a natural image. And you can see, I mean, we don't have a very skewed text here, but we still have an angle presence of, you know, like angle, and it's still doing pretty good job. Another, maybe, the last but not least important option I want to talk about is the padding. So when drilling down to the character level especially, and on the other levels as well, doesn't really matter. Based on the application and the custom need, one may need to adjust the padding and you know, like to, I don't know for what problem, for segmentation, for example. And actually you will be able to, you know, like now we're expanding, but you will be able to go down to the, you know, like up to the point size. So maybe if you need that for your application. Right, so I don't really want to talk much about the function because this is not designed, this is not, well, this is not ready yet, but let's see what we can use it for. So, oops. Okay, so let me show you something. So we have an office in Armenia, and so this is basically how our door looks. This is basically a normal, you know, like laminate door with a sticker on it saying like Wolfram Research and stuff. So what we can do, so first we can basically detect the text, and then we said we are doing it on levels. So say character level, word level, line level. And using that information, we can construct a small super function which will, you know, like generate a mask, binary mask for image, and allow us to segment the whole image instead of segmenting, you know, like characters, words, or lines. So just to give you an example of what this can be used for, is that we can tweak the color of the text on image, leaving the rest of the image untouched. But this is very, very basic and toy example, but this gives you an idea of a very basic, you know, like segmentation application using the text detection functionality. Another thing, okay, so another field that becomes, yes, of course. Another field that becomes reachable, let's name it this way, is car plate recognition. So you can see, I mean, like it's not like super accurate because these particular, you know, like networks that we use now, they are not exactly designed for car plate recognition, but as long as this can be interpreted as a natural image, it does a decent job. Not very accurate, but not 100% accurate, but still very decent job. I mean, you can see through a few images that the car plate recognition goes pretty well. And interestingly, it doesn't really care if, you know, like your car plate is a standard car plate or has, you know, multiple lines of stuff. Everything is being detected. And I mean, over here we have like a recognition going over, which is basically giving us the actual, you know, like car plate identifier. Right, so Another interesting field of application that can be utilized is basically analyzing business cards, because I mean, I personally have, I don't know, like tons of business cards gathered through my whole life, and if you ask me like who is there and where I got them from, I have zero clue. But what we can do actually is basically using you can use the like the semantic interpretation and the functionality of finding text to try to analyze your business cards. Basically, in this particular case, I'm just getting like who the card belongs to and what is the location associated to the card owner. I mean, it might be not present on the card. So, for example, you can see we have some of them, like without any identification. But if it is present, it will be identified. Right, okay, so I have 4 minutes left, and the last application and the most important one I want to talk about is basically creating a super function using the functionality of finding text. So what we are talking about. So let's basically first run through a very simple example. So we'll take an image. So we basically shoot a like short video, and this is a sample frame from that video. So as I said, I mean, for you to understand, so this is the corner line between natural images and scanned documents. So this is kind of because we have natural image and scanned text in it. So this is not a trivial image. So that's what I'm trying to say. So what we can do, first we can like get the data, which is in our case we're interested in like line-wise text detection and we are getting the aligned images out of it. Then we can use the functionality of text recognize, which is also being, like having a huge update in the next version, and is now way more accurate than it was before. And we recognize basically whatever is there. Now we can basically try to, like put all this information on a frame to imitate the effect of subtitle. So we create the subtitle which is basically, like taking the strings and concatenating them together. Then we can use another functionality of Wolfram language, which is basically text translation, and use the services to translate this to German. And all right, so it translated, and now we can use like old school rasterize this to get a graphics. Eventually, we can combine them, and like we will see now our text is like translated and rasterized there. So still nothing, like no need to hard code anything, everything automated. Next, we can find the face, and since like this guy didn't give you any permission to show his face, I have to close it. So last but not least, we can use audio, because we talk about audio a lot, and it will not be fair not to show that. And we can create a button, and you push on it, and nothing happens. Oh yeah, you have this off. No? Okay. No, we have to show this.
Yeah, we do.
I spent too much time preparing this.
No?
Now to lose.
No, we lose.
Okay, no, just take it out. Take it out.
No.
No, I will do this.
Oh, you're a genius.
I don't care.
Okay.
No.
Oh no, but it was to go on the built-in because it wasn't DisplayPort.
Not this one, not this
Yeah,
one,
yeah.
not this one. Not
Okay, let's try with the internal one. Headphone port. Yep.
My name is Fine Text.
Okay. Right.
My name is Fine Text.
No, we cannot. So, but it's too early for applause. Now, right. So we used some subset of functions, but we can extend it. I mean, we used only 10 or something, which is nothing for a super function. So we can add more, like video capabilities, audio capabilities, do anything out of core maybe.
Go to the other notebook.
Yeah, and eventually, so what you saw now, just to make this point clear again, so there is no hard coding, everything is being synthesized, everything is automatical. And you basically can do this whatever we did on a frame, on a video.
Hallo. Ik ben hier, die nieuwe functionaliteit in WL 12.1. Mijn naam is Vintext. Ik ben geschaffen, helfen Sie, tekst zu vinden afbeelden. Mijn altern zijn en helden en.
All right, so everything is synthesized here, so nothing is hard-coded or anything else. All right, so, yeah. So that's it, so thank you.